a video on matrix operations. We know what our number operations are and how they work, don't we? So we've got addition, so x plus y equals y plus x, that's commutative. We got subtraction, x minus y, and we know that is minus y minus x because it's not commutative, and we know that x times y equals y times x in ordinary numbers, don't we, because that is commutative. So question mark, do these exist in matrix operations and do they work? So let's have a look. Okay, so I've got two matrices here. I'm going to use some 2 by 2s, and can we add matrices? Is there such a function as summing? So m plus n, what's going on with that? So I'd start as ever with some expressions here. So 3x plus 2y, and I'm going to add that. So that'll be the upper line of my matrix. If I was doing the operation of that matrix times xy times the vector xy, and on the right hand side here I've got my vector, so my matrix 1 5 7 9, and I've got x and y there. So if I got these two expressions and I add them, well, I just get 4x plus 7y, and for the lower row 4x plus 5y, add it to 7x plus 9y, and I'm going to get 11x plus 14y. So I think that shows us, doesn't it, fairly quickly that I can add sum in effect to matrices. There are 3 2 4 5 here in the 1 5 7 9, and I will get 4 7 11 14. Yep, so here we go. So we've got matrix addition. In effect, m plus n has a meaning. Now let's have a think about commutativity. Well, what we just did is we did m plus n, didn't we? And we got this matrix here. Now if we do n plus m here, what are we going to get? Well, we get the same matrix. So m plus n equals n plus m. So as with addition in ordinary numbers, it's commutative. Yeah, there is a function and it's commutative. Now let's have a think about what we have to be able to add matrices. Well, we've looked above there at two 2 by 2 matrices, haven't we? So if I take that matrix and this matrix here and I put them in a normal sort of starting position with an xy vector, then we know that that's, from what we did earlier, is going to become a 2 by 2. And that's all fairly straightforward because I can put xy behind it and it all works. But can we do this for a matrix 1 5 7 9 there? So that's a 2 by 2, and can I add it to effectively a vector which is a 2 by 1? Well, I can't, because it doesn't make any sense if I put xy behind there and xy behind there. This one's okay, isn't it? Because I've got a 2 by 1. I've got a 2 row in the rows. I've got effectively 2 columns rather, and I've got 2 rows there, so I can do that multiplication. I can't do this multiplication here because I've got a 3 there. What am I going to multiply? I've only got one item there, haven't I? And I've got 2 here, so I can't really do that. I don't know whether this 3 applies to an x or a y, and I don't know whether that 4 applies to a 3, so it's an x or a y. So this one doesn't work. So to do addition, we have to have the same number of rows and columns in all our matrices. Yeah, I can add a 2 by 2 to a 2 by 3. I can add a 3 by 4 to a 3 by 4, but I can't add them if they haven't got the same dimensions. Okay, let's have a look at subtraction. Well, given what we just did on addition, we can probably see that if I've got 3x from the m vector here, I've got 3x plus 4y, and I'm taking away from the n vector 1x plus 5y, then what am I going to get left with? Well, in my x's, I've got 3 take away 1, so I've got 2 x's, and in the y's, I've got 2y take away 5y, I'm going to get minus 3. And doing the same below, we can see that that follows. So I think it's pretty obvious there that this vector, there's this matrix M there, take away the matrix N, and you just get the difference of each of the coefficients of the matrix, don't we? Yeah, 3 minus 3, take away 1 is 2, etc. all the way through. So that works, and that looks awfully like ordinary subtraction of numbers or differences of numbers. And what about commutativity? Well, if I swap these over and I've got n minus m, then I get the same values, don't I? But I get the negatives. Well, that's exactly what we expect to see in ordinary subtraction, isn't it? 5 minus 3 is the negative of 3 minus 5. Yeah, so that works like ordinary operation of numbers. But again, if we have a 2 by 2 matrix and we take away another 2 by 2, well, we know we're going to end up with a 2 by 2. But if I've got a 2 by 2, I can't really take away a 2 by 1 because I'm not sure which column to take it away from. I could try and take it away from both, but it wouldn't really work because if I put x, y behind it, this makes no sense. Yeah. So they must have the same number of rows and columns, the same dimensions to be able to do subtraction or differences. Did a separate video on multiplication in which we looked at the fact that how the operation works. So if I've got these same two matrices m and n, we multiply them, then as long as we've got the same number of columns and rows, it works between those two, isn't it? So 3 times 1 and 2 times 7 gives us our 17 over here. So that's mn. Sometimes people put a dot between them, most of the time they don't bother. But let's have a look at commutativity then. So here's mn would give us this matrix here. If I multiply n by m, so I've changed the order, I get a different value here because if I take this first row, and multiply it by the first column, I've got 1 times 3 and 5 times 4. That gives me 23, not 17. So unlike ordinary multiplication, 3 times 2 equals 2 times 3 is commutative. It's not commutative with matrices because I get a different answer if I multiply m by n, m dot n, than I will if I do n dot m. So they're not commutative. Second thing we need to think about is conforming matrices. Well, we were quite happy that we could multiply above a 2 by 2 matrix by another 2 by 2 and we get the resultant is a 2 by 2. And we also looked before at multiplying a 2 by 2 matrix by a 2 by 1 vector, and that worked. So let's just have a reason for that. I'm going to take that row and I'm going to multiply it by this column. Now this has got 2 items in it and this has got 2 items in it, so that matches up for the operation, doesn't it? Because I'm going to get 3 by 1, 3 times 1, and add it to 2 times 7. So that one's going to work, isn't it? And let's have a think about playing around with this. What if I had a 1 by 2 vector there, coordinate vector, and I'm going to multiply that by a 2 by 3 matrix? Well, again, if I look at that column there, that row there, it's got 2 items in it, 3 and 2, and I'm going to do the operation with that first column. It's got 1 and a 7 in it. Well, that's okay, isn't it? Because I've got 2 items in each, so I've got 3 times 1 and I've got 2 times 7, and that added together is going to give me 17. And then I can do the same with the next column, and then I can do the same with the next column. So I'm going to end up with 1 row and 3 columns. So let's have a look at where that comes from. Well, the 1 row comes from this left-hand matrix vector, isn't it? Because it's only got 1 row in it, and our answer's got 1 row in it. And where did the 3 columns in our answer come from? Well, they come from the fact that I've got 3 columns in the second matrix. Yeah, so that 3 comes across, gives us that 3 there, and this 1 gives us that 1 there. What we do need, so this 2 disappears in the operation, but they must be the same for us to be able to do the operation. Yeah, the fact it was a 2 and a 2 and made it possible in exactly the same way here, that the 2 and the 2 there in this example up here make that possible, and then the 2 here, because we had 2 columns in our matrix, gives us our 2 columns in our resultant vector, and the fact we've got only 1 column in our vector here gives us our 1 column here in this final vector. So that's how things must match up for us to be able to do multiplication. Let's have a look at one that doesn't work. So if I took a 2 by 3 matrix and tried to multiply it by this 1 by 2 vector, this isn't going to work because I've got 3 coefficients here and I'm trying to find 3 values in my column to multiply them by, isn't it? Because I'd have to have a 1 by 3 and I have to have a 5 by something and a 4 by something. Now I can't do that because this 3 for the number of columns in my matrix over here doesn't match with the fact that I've only got 1 row there. So that doesn't work. So this must be the same. So the number of columns in our left-hand matrix must equal the number of rows in our right-hand matrix for us to be able to do multiplication. I'm not going to deal with division, which is the inverse of multiplication, because I've got a separate video for that. But what we have convinced ourselves of is there is such a thing as addition and subtraction, and that they are the same, and they're associative and distributive as well as commutative. When it comes to multiplication, for addition and subtraction, though, we must have conforming number of the dimensions, i.e. rows and columns. For multiplication, well, we find that whilst it exists, it's not commutative, and we also know that we must match up again there, that the number of columns in the left-hand matrix must equal the number of rows in the right-hand matrix for us to be able to do multiplication, but it's not commutative. And division I'm going to deal with in another video. So there we are, the basic operations.